Okay, in this video we're going to continue talking about inverse functions, and we're going to talk about finding the inverses of power functions and also using something called the horizontal line test on these functions to tell whether the inverse would also be a function. So let's get started with kind of a straightforward example, hopefully. Let's look at the function f of x equals x squared. Now, if you can use your graph paper to do this lesson, that'd be ideal, because what we're going to do is we're going to take a look at some graphs, and we're going to actually graph f of x equals x squared, and then we'll take a look at its inverse. Now, if we were to graph this, we can make a table, and some values we might plug in would be 0 for x, and if we squared 0, we'd get out 0. So if we had a plot a point, that would be the origin, right? If we plugged in 1 and squared it, we would get 1. So I would plot this point, and if I plugged in 2 and we squared it, we would get 4. So if we plugged in 2, we'd get out 4. And of course, we can plug in the opposites there, right? We can plug in -1, and if we square -1, of course, you get +1. So we can plot a coordinate there. And if we were to plot -2 and squared it, we get +4. So we get a nice parabola, U-shaped graph. So if I had to just draw a sketch, hitting those points, not the greatest line there. Let me try that again. Come down, hit the origin, and then come up through. There we go. So we get the following graph. Now, if I wanted to do the inverse relation, let's maybe use red. Hopefully this shows up well. If I wanted to do f inverse of x, remember what we did last time is we just switched the x and the y values, right? So if I did that, the old y values, or the original range, becomes the domain of the inverse. So I would have 0, 1, 4, 1, 4, and then the corresponding outputs for those inputs would be the original domain. So 0, 1, 2, -1, -2. Now if we plotted the inverse on the same graph, something interesting happens, and you'll notice in a second. If you plot 0, 0, still have that same coordinate, 1, 1, still right there. And then if we plotted 4, 2, that would be right here. If I can get it to work, there we go. And if we plotted, it's also saying if we plot -1, we would get -1, so that would be that coordinate. And then if we plot 4, we would get -2. So our graph here would look something like this. Now, the inverse, if you take notice, this is not a function, because if we were to use that vertical line test, I hit that line more than once. So the inverse, this is not a function, because it fails the vertical line test. And you can also look at the table of values. I have the input 1, for instance, giving me an output of 1, right? And it's simultaneously, I have the same input 1, and it's giving me a different output, -1, and that violates the definition of a function. We can't have the same input with two different outputs. And another way of looking at it graphically is it cannot have a horizontal line hit any point or any part of the graph more than once. So the inverse is not a function. So the thing that we have to be careful about, guys, when we do the inverses of these types of functions, we have to be careful about the domain. So in order to make this actually become a function, what the book does, and what I will do is, I might say the following. We're going to find the inverse of f of x equals x squared if the domain is x values bigger than or equal to 0, for instance. Now, what that means is the following. If we were to look at it graphically, I'm saying that I'm only allowed to plug in x values that are non-negative, or basically 0 or larger. So if we did that, okay, this graph would no longer be a full parabola. We'd have to take away all of these negative inputs, and we would just be stuck with that positive part. What that means is that would take away these negative inputs here on our table and these outputs that came with it, and therefore it would also take care of these parts, or this part of the inverse. And so the only points we would have been able to plot would have been 0, 0, 1, 1, and 4, 2, which is the top part of that inverse. Now, if we were to draw that vertical line, you can see it only hits one part, and it's now a function. So that's what we'd have to do. We have to kind of restrict the domain so that we don't run into this problem about the inverse being a function. So what you might do then is just like what we did before. Remember, f of x is really just y, right? So I can write this as y equals x squared. And if I were to find the inverse, this is where we switch the x and the y, and I'd get x equals y squared, and we can solve for y. Now, if I were solving for y, I would have to square root both sides of this equation. And if I did, I would get y equals plus or minus the square root of x. Now, we have a choice to make here. We can't have both positive and negative for the square root of x. And how you're going to figure this out is as follows. Keep in mind, the original function had this domain, right? This was telling us what values we were allowed to plug in. If you remembered from the last video, the domain of the original function, right, of f of x, should be the same exact thing as the range. Man, I'm having a hard time having this thing right now. Should be exactly the same thing as the range, if it will write, of the inverse function. Guys, range, remember, has to do with outputs, right? So we have to guarantee right now, if I can write outputs, this pen is just not working for me right now. We have to guarantee outputs, right, of our inverse that are going to be positive or greater than or equal to 0. So if I had to make sure that this is going to be positive, these outputs, I want to choose the positive square root of x and not the negative. So my final answer here, I would say, all right, the f inverse of x is going to be the positive square root of x. That would guarantee that the range, this range, the outputs, is also going to be bigger than or equal to 0, much like the domain of the original function was. And if you take a look at what we have graphed in red, these range values, these outputs are bigger than or equal to 0. These are all positive or 0 outputs on that red line there. One other thing before we leave this example alone that I kind of want to talk about is this. There's a shortcut you could use if we were to have graphed the entire original function. Remember how we had this parabola? I'm just going to sketch it like that. And our inverse really, if we didn't restrict the domain, our inverse looks something like this. And remember how we talked about it failing the vertical line test? So we decided that this inverse is not a function. What's kind of cool is there's a shortcut to knowing whether or not a function has an inverse that is also a function. And you don't have to graph the inverse to do it. What I could have done instead is I could have done something called the horizontal line test, which is where you take a horizontal line and you try to see if you can pass it through the original function. Remember, this is our original function, f of x, that parabola. If a horizontal line hits your function more than once, that would mean it would happen if you were to graph the inverse, a vertical line would hit more than once as well, and therefore make the inverse not a function. So let's summarize that. Let me go to another page here. So the horizontal line test goes like the following. So horizontal line test is just saying the following. If a horizontal line, line crosses the function, the original function f of x, or the original function, more than once, more than one time, then the inverse for f of x is absolutely not a function. And that is going to come in handy later on when we look at just graphs. I'm going to do one more example with you, and then we'll talk about maybe some example problems for you to try. Let's do example 2. Let's find the inverse. Find inverse function of, let's do f of x equals, let's just do something simple. Let's do x cubed. Okay. Now, what I could do first is, it's not going to be hard. If we were to sketch a graph of f of x equals x cubed, if we made a quick table, if you plug in 0 and cube it, you get 0, so we can plot a point at the origin. If you plug in 1 and cube it, you would get 1, so we can plot a point there. And if you plug in 2 and cube it, you would get 8. So that would be, let's just say that that's 8. We're just drawing a sketch. If we plugged in -1, we can get an output of -1, so that would be right there. And if you did -2 and cubed it, we would get a -8, which would be down here. So our graph for this cubic looks something like this. Again, this is just a sketch, right? Not perfect. Real quick, does this pass the horizontal line test? If we put horizontal lines through here, does it hit more than once? No, right? We only hit once each time. So that means, if I were to ask, that means that the inverse, f inverse of x, is a function as well. So is a function, and I don't even need to graph the inverse of x. I already know, because the original passes, that means the inverse will be a function. To continue, let's actually find the inverse function for f of x. Now remember, if we want to find the inverse function, let's first start off by using the notation y equals x cubed rather than f of x equals x cubed. And what I'm going to then do is switch x and y. So I have x equals y to the third, and now I'm going to cube root both sides. I'm going to actually use the radical notation this time, so I'm going to make the index 3 and cube root. And remember, when you do cube root, you don't need plus or minus, so I end up with the cubed root of x equals just y. And your final answer then, if we use the correct notation, would be f inverse of x equals the cubed root of x. For this last example that I'm going to do with you, I want you to find the inverse of f of x equals -3 minus 5x to the fourth, given the domain x is less than or equal to 0. So remember, when you get that little extra statement there, that's really just telling you your domain. And already, when I get that domain, what I'm thinking is, first of all, if I can write with this thing, that would be nice. The domain of the original is going to be exactly the same as the range of the inverse. So I'm going to keep that in my back pocket as I solve this thing, and I know I'm going to end up using the fact that the range of the inverse also has to be less than or equal to 0. These have to be numbers that are going to be non-positive or negative numbers including 0. So let's find the inverse first by rewriting this as y equals -3 minus 5x. Let's make that a 5x to the fourth. And then we switch the x and the y. So I get x equals -3 minus 5 y to the fourth. Now I got to solve for y, right? So the first thing we should do is add 3 to both sides. So now I have x plus 3 on the left equals negative 5y to the fourth power. Now what I'm going to do is I'm going to divide both sides by a negative 5. And then I have x plus 3 all over negative 5 equals a y to the fourth. Now what I'm going to need to do is fourth root both sides. So I'm going to fourth root over here. I'm going to fourth root over here. And so on the right side we now just have y. And on the left side, whenever I do it any even root, I have to remember a plus or minus. Now, what this plus or minus does is guarantee that the outputs are either going to be positive, if we choose the positive, or they're going to be negative outputs if we choose the negative. This is where I'm going to go back to the original domain statement here that told me the inputs for my original function have to be less than or equal to 0. That means the outputs of my inverse function also have to be less than or equal to 0. And in order to make that happen, I'm going to choose the negative, not the positive. So my final inverse function is going to be the negative fourth root of x plus 3 all over negative 5. And so what we really have here then is the inverse function f inverse of x is the opposite of the fourth root of x plus 3 over negative 5. And that's about as complicated of an inverse function to get that I'd ever ask you to find. Now I would like you to try the last couple problems as a self-quiz. So for number 1, I would like you to find the inverse for f of x equals x squared plus 1 given the domain is x values greater than or equal to 0. And for number 2, I want you to graph f, this function down here, graph f of x, to determine if its inverse is also a function. And if you remember, I did something similar in one of my previous examples, and my hint to you is to use this horizontal line test. So if you apply the horizontal line test correctly to the function, you should be able to tell whether the inverse is also a function. So please try those, and we'll see how we do tomorrow. Thanks for watching.